Welcome to the Explainer, everyone. Today we're going to break down the completely invisible, yet incredibly powerful fundamental forces that govern absolutely everything moving around us. And I mean everything, from a simple rolling ball on the floor to a massive speeding car on the highway. You know, whether you realize it or not, every single time you take a step, or drive to work, or even just accidentally drop a pen off your desk, you are actively participating in a beautifully precise set of rules that the entire universe follows. We interact with these rules so constantly that we take them for granted. So today, we're going to change that. We're going to pull back the curtain and make those invisible rules visible.
Okay, so let's dive into this logical journey together. Here is our roadmap. We are going to build this up step by step. We'll start with the fundamentals of force, unpack the really fascinating concept of inertia, dive deep into momentum and the math behind it, look at some really cool real-world applications, and finally, wrap the whole thing up with friction and circular motion.
All right, Section 1, Fundamentals of Force. What actually makes things move?
To truly understand motion, we have to start with the absolute most basic building block of mechanics, force. Force, simply put, is the external agent that interrupts an object's inherent laziness. It is a push or a pull that results directly from an interaction with another object. We measure this force in newtons, and it's represented by the famous formula, F equals ma. Now here's the key takeaway. If you want to change an object's state, whether it's just sitting there minding its own business or if it's already flying through the air, you absolutely must apply a force to it. There's no getting around it. But, and this is crucial, not all forces actually cause motion. And that brings us to a really important distinction we need to make.
Take a look at a simple resting book on a table, for instance. Right now, there are forces acting on it, but they are perfectly balanced. The book is being pulled down by the invisible hand of gravity, sure, but the rigid table is pushing back up with an equal and opposite normal force. So the net force is exactly zero. It's a physical tie, so the book stays exactly as it is. It goes nowhere. But think about what happens when your foot hits a stationary football on the grass. In that split second, the forces are definitely no longer equal. That sudden, unbalanced force from your foot is practically demanding a change. That unbalanced force is strictly required to actually cause acceleration, to force the ball to change its state of rest and shoot across the field.
Which brings us to Section 2, inertia and the first law, the resistance to change.
So, now that we know what a force actually is, let's look at how everyday objects naturally try to resist it. This is a concept Sir Isaac Newton called inertia, and it is the beating heart of his first law of motion. You see, physical objects are fundamentally stubborn, and they're stubborn in three very specific ways. First, there's the inertia of rest. This is a body's tendency to just stay parked. If it's sitting still, it wants to keep sitting still. Second, we have the inertia of motion, which is the tendency for an object to keep moving at the exact same speed if it's already moving. It doesn't want to speed up, and it doesn't want to slow down. And third, the inertia of direction, meaning a moving object just wants to keep going in a straight, unchanging line. The crucial point here, the big takeaway, is that an object will only ever change its state if an external, unbalanced force literally forces it to. And by the way, the more mass an object has, the more inertia or sheer stubbornness it possesses.
Now, you might be thinking this all sounds a bit abstract, but I guarantee you felt this exact physics principle in the real world countless times. Think about being on a city bus. When that bus suddenly accelerates forward, what happens? Your body, which was previously at rest and wants to stay at rest, suddenly feels like it's falling backward. That is the inertia of rest in action. Or think about when you're riding in the passenger seat of a car that takes a really sharp turn at high speed. You instantly feel pushed toward the outside door, right? That's because your mass wants to keep moving in a straight line. That's inertia of direction, but the physical car is turning around you, pushing into you.
Let's move on to Section 3, momentum and the second law, the math behind the motion.
Okay, so what actually happens when an unbalanced force finally wins that tug of war and an object moves? To really grasp this, we have to talk about momentum. Think of momentum as the actual quantity of motion an object possesses. It's a package deal, a combination of two things, an object's mass and its velocity. So first we have what we call the mass effect. This tells us that stopping a heavy, slowly rolling garbage truck requires vastly more force than stopping a lightweight toy car rolling at the same speed. That's pretty intuitive. But then we have the speed effect. This explains why stopping a tiny, practically weightless, but incredibly fast-moving bullet requires an immense amount of stopping force. Both the mass and the speed combined dictate exactly how much force you are going to need to alter that object's path.
Let's see how these concepts build into arguably one of the most famous equations in all of physics. And don't worry, this isn't just some abstract math equation floating on a chalkboard, it's a completely logical recipe derived directly from Newton's second law. The law simply states that force is directly proportional to the rate of change of momentum. So let's spell that out. Change in momentum over time gives us mass times the change in velocity, all divided by time. Now here is where it clicks. The change in velocity over time, that is the literal definition of acceleration. So we just substitute the letter a right into the equation. Just like that, the formula beautifully and elegantly simplifies down to F equals ma. Force equals mass times acceleration. This incredible little equation tells us exactly how much force is required to change an object's momentum. It is the master key to mechanics.
Section 4. Conservation and Applications. Putting the laws to work. Let's see how all this theory actually looks in practice.
Take a look at this setup. This is called an Atwood machine. It's a classic physics apparatus featuring two different masses hanging over a smooth, frictionless pulley. Now, because the masses are different, Earth's gravity pulls down on the heavier one harder than the lighter one. This creates exactly what we talked about earlier, a completely unbalanced force. But what is truly brilliant about this system is how we can take that simple F equals m formula we just unpacked and apply it to both masses simultaneously to figure out exactly what's going to happen. By setting up basic equations for both of these hanging masses and factoring in the tension of the rope that connects them, we can elegantly isolate our variables. Through a simple mathematical substitution, we can calculate the exact acceleration of the entire moving system, as well as the exact tension pulling taut on that string. It's just amazing. It's Newton's laws perfectly and reliably predicting a complex real-world mechanism before it even moves.
Finally, Section 5, Friction and Circular Motion, the invisible forces of turning.
For our final and arguably most complex building block, we need to introduce a new force that actively opposes motion. Have you ever wondered why it's incredibly hard to get a heavy living room couch to start moving, but once you finally get it going, it's actually noticeably easier to keep it sliding across the floor? Well, it's all about microscopic interactions. Even the smoothest-looking surfaces are jagged at a microscopic level. When a heavy object sits on a surface, the tiny microscopic irregularities of both materials settle into each other. They essentially lock together, a phenomenon often referred to as cold welding. This creates what we call static friction. Now, limiting friction is that agonizing peak threshold. It's the absolute maximum force required to just snap those little microscopic junctions and initiate movement. But once that couch is finally moving, the surfaces are sliding past each other too quickly. They simply have much less time to form those strong interlocking bonds, meaning the opposing force drops. That new, smaller opposing force is your kinetic friction.
So what happens when we combine these opposing forces with a change in direction? When an object travels in a circle, like a tetherball on a string or a race car on a track, its direction is constantly, continuously changing. And what did we say earlier about the inertia of direction? Objects always want to move in a straight line. Therefore, if it's going in a circle, an inward push or pull is continuously required just to keep it from flying off in a straight tangent. This mandatory inward force is called centripetal force, and it always acts dead toward the center point of the circular path.
So how does this abstract physics concept apply to our everyday life? Well, think about when engineers design curved highways. They don't just lay the asphalt completely flat, do they? No, they explicitly bank the pavement at an inward angle. Why? Because they want to utilize multiple physical forces at once to keep you safe. To calculate the exact right angle, engineers rely on a beautiful, rather complex equation that dictates the absolute maximum speed a heavy vehicle can travel on that curve without skidding outwards into the barrier. By banking the road, a specific component of the normal force, literally the physical road pushing back up against the weight of the car, is angled directly toward the center of the turn. This ingenious angled push, combined with the static friction of your rubber tires gripping the asphalt, provides that necessary inward centripetal force we just discussed.
As we've clearly seen throughout this explainer today, everyday motion isn't just some random occurrence. It is a tightly choreographed, utterly predictable dance of balanced and unbalanced forces, of inertia, mass, and friction. Now that you know the invisible mechanics pulling the strings behind the scenes of our universe, how will you see the world of motion around you differently? Seriously, the next time you're cruising on a highway and you safely navigate a sharp curve in a speeding car, who are you going to thank? Will you thank the gripping friction of your tires, or the careful, calculated banking of the road itself? Hopefully, after today, you'll realize it's the perfect physical combination of both working to keep you safe. Thanks so much for joining me on this explainer, and keep looking for those invisible forces in your own life.